Hi everyone. So today's lecture is going to be about attention mechanisms in deep learning. Before we dig into the details of attention, let me cover the outline of the presentation. I will start with some motivating examples, followed by an overview of attention. Then I will introduce attention in details and go over each one of the main components of these mechanisms. Once we have a good idea on all the attention components, we will see instantiations of those on different application domains, starting from neural machine translation, where we will focus on 2 examples of attention, followed by 3 computer vision applications where attention has shown to be a useful tool, and closing with attentions in graph structured data as a way to emulate convolutions. Finally, I'll wrap up the presentation with a summary of the materials. Let's start with the motivation and overview. Before digging into the definition of attention mechanisms and how they have been applied in the deep learning literature, let's start with some motivating examples as to why attention may be beneficial for different tasks. Let's consider the task of describing an image. So if I show you this first picture on the left, one way of describing it would be to start by focusing on the 2 polar bears that appear in the middle of the scene. We could maybe mention that the one on the right is sitting, whereas the one on the left is standing. Then we could maybe focus on different parts of the scene, highlighting the snow around the polar bears and maybe even the snow and the sky on the background. If I were to show you this second picture, one possible way of describing it would be to focus on the central dish, so carefully going over the ingredients that we can see and eventually redirecting our focus to different parts of the image, maybe highlighting other dishes or providing a description of the table on the background. In both cases, however, we would be describing the picture by focusing on different parts of the image sequentially. So while describing the bears, we would be concentrating on the central part of the image. And while describing the dish in the second picture, we would be focusing on the visible ingredients one at a time. And so we would be glancing around different regions of the image and paying attention to different parts of it as we describe them. Following up with a different example where we would want to predict the ending of the 2 sentences on the slide. Similarly to the image description case, we would be selecting the most pertinent piece of information to come up with the missing words. And so in the first case, we would probably agree that train station is the most relevant cue in order to infer the missing word, which is train. In the second case, we could probably focus on the word doorbell in order to infer that the missing word is door. And so overall, not all words in the sentence would be equally important in order to determine what comes next. So as we have seen in the previous examples, we would describe scenes or complete sentences by paying attention to different parts of the input, so the image or the sentence, and focusing on the relevant bits of information in order to perform the task. So attention mechanisms make use of these previous observations, so the observation that different parts of data might have different relevance, and allow us to selectively concentrate on a subset of information, presumably the most relevant piece of information, while ignoring other parts. Attention mechanisms are currently widespread in the deep learning literature and have been exploited in many application domains and in conjunction with many architecture types. In particular, attention has been coupled with recurrent neural networks, convolutional neural networks, but also used standalone. Examples of application domains include image captioning, where we need to provide a sentence describing the input image, or neural machine translation, where we are provided with a sentence in one language, and the goal is to output a sentence, the translated version in another language. We also have the application of image to recipe generation, where we are provided with a food image, and the goal is to obtain the recipe from it. But also graph neural networks, where attention has been used as a way to emulate convolutions. So those are just a few examples on application domains that have benefited from attention. And this is to say that attention can be applied to many different kinds of data. So let's move on and dig into the details of attention mechanisms. As we have seen, attention can be applied to many application domains, regardless of the kind of data. Attention mechanisms can be decomposed into two steps. The first step takes some inputs and predicts the attention weights. And the second step performs an aggregation operation, which results in the attention output. In this presentation, we will focus on one particular kind of attention called soft attention. And taking this into consideration, we will define the details of both the extract weights function and the aggregate function in the next few slides. So to define what's going on in each one of the attention steps, we will use the image captioning example. So if you recall, in image captioning, we are given an image, and the goal is to predict the words forming a sentence which best describe the image. And so every time we predict a word, we may be focusing on a different part of the image. So in this case, the first step of the attention mechanism, so the extract weight function, should tell us where to focus, and more generally with which strength we should focus on each part of the image in order to predict the next word in the description. So in order to determine this attention strength, the extract weights function takes as input a set of image patches. So here, those image patches come from the grid depicted on top of the image. And we could either use these image patches or some features extracted from those. The function would also take as input a representation of the words predicted so far. And the goal of the extract weights function would be to compute how much focus to assign to each image patch, considering that what we have described so far. As a result, the function would output a weight for each considered input patch. In practice, these input patches are referred to as keys or annotations. The incomplete image description is referred to as query or context, and the output of the function is referred to as attention weights. So once we have the attention weights, we can perform the aggregation operation. And so the aggregate function takes as input the attention weights and what we call values. That is where we want to apply our attention weights. Following up with the previous example, that would be the initial image patches or the corresponding features extracted from those. Note that in this example, as well as in many applications, keys and values are equal. However, this does not have to be necessarily the case. One could use different information to define keys and values. So the aggregate function combines the information from different image patches by assigning them different weights, and so different levels of importance. This procedure can be applied multiple times and can be followed by any other operation in order to predict the next word in the description. So in the next few slides, we will detail the operations of the extract weights and the aggregate function. So let's dig into the details of how to compute these attention weights. Going back to the extract weights function, let's recall that as inputs, we have a set of keys that are denoted by h sub k. So we index with the subscript k, and a query denoted by hq. The output of the function is a set of attention weights or coefficients, which we denote as alpha subscript k. Note that the cardinality of the set of keys is equal to the cardinality of the attention weights. And so we start by combining each key and query within a function that is parameterized by theta. And this function f, parameterized by theta, is usually modeled by a neural network. This function is applied to each key query pair, and the parameters of the function are learned by means of backpropagation. The function f computes a score, which we denote e subscript k, for each key query pair, and we will see examples of instantiations of this function f later in the presentation. This function is sometimes referred to as a scoring function. Once we have all the scores, we apply a softmax nonlinearity. This allows us to obtain the so-called attention weights, and this is in the context of soft attention. Note that in this case, the attention weights are bounded between 0 and 1 and represent a probability distribution over the scores. Finally, the extracted attention weights are combined with the values in the aggregate function. In particular, each value is multiplied by its corresponding attention weight, and then the scaled values are aggregated by means of a summation. So this slide actually concludes the introduction of attention mechanisms, and what comes next is just how this mechanism is applied in different application domains. In particular, we will see different instantiations, different examples of query keys and values, and also different scoring functions, which have been successfully used in the literature in different tasks. So in particular, we will focus in the task of neural machine translation, then in computer vision tasks such as image captioning or image to set prediction or image to recipe prediction, and finally in the graphs domain. So let's start with the applications of attention. If we start with the example of neural machine translation, let's start by defining what neural machine translation is. So neural machine translation consists in translating text from one language to another using neural networks. Neural machine translation has long relied on encoder-decoder RNN architectures and their variants such as LSTMs or GRUs. I will take a very brief detour to review what RNNs are. So RNNs allow neural networks to work with sequences of data like text and videos. And this kind of neural networks allow reasoning about previous information. In particular, a neural network here, which is denoted as NN, looks at some input at time step t, so for example, x1, and outputs a value y1. This happens at multiple time steps, so each step takes as input an element of the sentence, collects information, and propagates it to the next step. The information propagated between different time steps is the hidden state of the RNN, which is here denoted as S subscript the time step. This propagation of information from one step to the next allows the information to persist through time. So now that we have reviewed standard recurrent neural networks, let's see how these encoder-decoder RNNs of neural machine translation look like. The encoder RNN is used to process the entire input sentence, so the sentence in one language, and it encodes it into a fixed length vector. The resulting vector, which corresponds to the last state of the RNN, in this figure here, depicting the states of the encoder RNN with the letter H. So this last state of the encoder RNN is expected to be a good summary of the input sentence and is used as initial state for the decoder RNN. The decoder RNN is used to predict the translated words one after the other. In this case, the hidden state of the decoder RNN is denoted with the letter S. The problem with this kind of approaches is that they rely on capturing all the relevant information in a single state, which is the final state of the encoder RNN. And so as sentences get longer, it becomes more challenging to obtain good summaries. In fact, recurrent neural networks suffer from temporal dependencies, and so their performance usually degrades rapidly with the length of the sentence. So to solve the encoder-decoder RNN bottleneck problem, researchers have proposed to use attention mechanisms. With attention, we avoid the information bottleneck by not trying to encode the full input sentence into a fixed length vector. So instead, what we do is use all the states of the encoder RNN as input to the decoder RNN. So we will use so as I mentioned, we will use all the hidden states of the encoder RNN, and we will apply some attention weights to those. So now at each time step, the decoder RNN will look at all the encoder hidden states. Given each hidden state, it will compute an attention weight. Then it will multiply each hidden state by its corresponding attention weight and aggregate all the resulting information to condition the prediction of the next word. So at each time step of the decoder RNN, we will have as input the output of the attention over the encoder RNN hidden states and the hidden state of the decoder RNN. In this case, if we go back to our initial definition of attention, our scoring function, f, will take as input the current hidden state of the decoder RNN as well as each encoder RNN hidden state. And so more precisely, our query here will be the decoder RNN hidden state at time step t-1. Our keys will be the encoder RNN hidden states. We will get scores and so attention weights for each query key pair, and our values in this case will be the same as our keys. And so we will apply our attention weights to the encoder RNN hidden states directly. The scoring function f, in this case, is modeled with a feed-forward neural network. Although the previous method was the first one to successfully apply attention to neural machine translation problems, since its inception, there have been other forms of attention mechanisms that have been proposed in the literature. One noticeable example of this is the transformer model that is also an encoder-decoder model, but which is solely based on attention mechanisms. So there is no RNN whatsoever here. This makes the model more parallelizable and so has the potential to save significant training time. In the case of the transformer, the encoder is composed of what we call a self-attention block followed by a feed-forward neural network. The decoder is composed of the same kind of self-attention block and is followed by an attention block where the output of the encoder interacts with the information in the decoder. And finally, we have a feed-forward neural network. Note that in practice, to increase the model capacity, we can stack multiple encoder and decoder blocks. Now let's see how those self-attention and attention operations look like. So before we start introducing attention and self-attention, let me note that self-attention and attention only differ in their definition of keys, queries, and values, and hence follow exactly the same operations. So starting from our usual query and keys, we transform them by means of a feed-forward layer or network. Then we can combine the transformed queries and keys by applying a scaled dot product operation. This results in what we have previously introduced as scores. Once we have all the scores, we apply a softmax nonlinearity as described in the attention overview. And this allows us to obtain the attention weights. Once we have the attention weights, we can combine those with, in this case, transformed values in the aggregate step. And so when it comes to self-attention, we will use as query words from the input sentence, keys as words from the input sentence, and values, for the values, we will use the same as for the keys. The same applies in the decoder. In the decoder case, the query will be words from the output sentence. The queries will be words from the output sentence as well, and the values will be the same as the keys. So in self-attention, we have queries, keys, and values being the same. However, in the attention case, we will have as query words from the output sentence. As keys, we will have words from the input sentence this time, and as values, we will use the keys again. So as mentioned before, the output of the scaled dot product corresponds to the scores. And so our scoring function f, parameterized by theta, corresponds to the blocks highlighted within the purple box. So in this case, it consists of two transformations that we apply to the queries and the keys, followed by the scaled dot product. To make this more concrete, the f function scores each word of the input sentence against a query. So in this case, the query is a word of the input sentence in the case of self-attention, or a word from the output sentence in the case of attention. The scores computed by the function f are fed to the softmax nonlinearity to determine how much focus to give to other parts of the input sentence. And if we contrast this with the previous model, the one that was based on encoder-decoder RNNs, which used the hidden state of the RNN to collect the information about the previous words. In the transformer, self-attention is the operation which allows to collect information from other relevant parts, relevant words of the sentence. So that was it for neural machine translation. And so moving on to some computer vision applications, attention has been used for image captioning. In this task, remember that the goal is to describe an image with a sentence. And again, encoder-decoder architectures are also ubiquitous. So since we are dealing with images, in this case, the most common encoder architecture is a convolutional neural network. So we start by feeding an image to a convolutional neural network and extract a set of features, which we depict here by means of the blue squares. Attention is then applied on these extracted features. So the output of the attention is, in this case, used to condition each step of the image description prediction. The image description predictor is performed by means of a decoder RNN. So this part should be very reminiscent to the first example of the neural machine translation, with the difference that instead of using an encoder RNN, we're using a CNN encoder, and we are applying the attention on top of the extracted features from the input image. In this case, we define the query as the decoder hidden state at time step t-1. The keys are the set of extracted image features, and the values are again defined as the keys. And so in this case, the scoring function takes as input the hidden state of the decoder RNN at time step t-1 and some image features. Once again, F is modeled by a feed-forward neural network. Attention has also been used for image-to-set prediction. This task is also known as multi-label classification and consists in finding the set of labels which best describe the input image. So you have an example here of the image that we have been seeing throughout the presentation, and maybe some labels that would be assigned to this image would be polar bear, snow, and sky. So in this setup, since we are dealing with images, we also have an encoder-decoder architecture, which leverages a convolutional neural network as feature extractor. In this case, the features extracted by the CNN are fed to a transformer decoder. The transformer decoder predicts the labels describing the image. In this case, the attention query is the predicted label. The keys are the image features, and once again, values and keys are equal. In the self-attention part, the query corresponds to the predicted label, and the keys to the predicted labels as well as the values. So again, note that self-attention uses the same as query keys and values. The scoring function of this model is the one that we have initially introduced in the transformer. So recall that was the transformation using a feed-forward network of keys and queries followed by a scaled dot product. A third application in computer vision is the one of image to recipe generation. That is writing recipes from food images. Once again, we have an encoder-decoder architecture where the encoder is a CNN to extract image features. In this case, the CNN is also supposed to predict the ingredients that are present in the input image. And so we use the CNN as feature extractor as well as ingredient predictor. So once we have predicted the ingredients, we use both the predicted ingredients and the features extracted from the image and concatenate those in order to feed this concatenation to a transformer-based decoder. This transformer-based decoder is responsible for generating the recipes. So again, we have this transformer-based decoder. So we have the self-attention and the attention modules. And so in the self-attention models, query keys and values are the same and correspond to the output sentence. So the sentences of the generated recipe. Whereas in attention, query corresponds to the words or word embeddings from the output. So the generated recipes, the keys are the ingredients and image features, and values and keys are the same. Again, note that the scoring function used in this pipeline is the one introduced in the transformer. So that is the feed-forward transformation of keys and values followed by the scaled dot product. So finally, let's see how attention has been used in the graph domain. So in this case, attention was introduced as a way to emulate convolutions. As a reminder, this is how convolutions look like in the image domain. So given an image, we slide a filter over the image, at each position, we multiply the filter values, which we denote here with alpha, with the image features, which we denote with H. Then we aggregate locally via summation, and eventually we can then apply a nonlinearity denoted here as sigma. So how do we apply convolutions on graphs? So say that we want to update the features of the blue node. Following the convolution operation that we have seen in the previous slide, we would take into account the features of the blue node as well as the features of its neighbors, here depicted in green. The caveat here is that each node may have a different number of neighbors, a different degree, and so we need to be able to account for that when designing the convolutional operator. So attention has been proposed as a way to emulate convolutions, which is able to handle nodes with different degrees. And so in this case, we reinterpret the convolution operation from the previous slide, but from an attention perspective. So in this case, alpha corresponds to the attention weights, as opposed to the filter values in the previous slide, and H subscript n correspond to the values that we will feed to the attention mechanism. In this case, the values would correspond to the node features. And so in order to obtain the attention weights, we define a scoring function modeled with a feed-forward neural network, which uses as query the features of the blue node, as keys the features of the nodes in the neighborhood of the blue node, including the blue node itself. And as values, we use the same as what we use as the keys. So given this formulation, the same procedure is applied to all nodes. And the potential of this kind of operator, which was introduced as the graph attention networks, was tested on several node classification tasks. So to wrap up this presentation, we started with a brief introduction where we had some motivating examples, and we saw an overview of application domains where attention was successfully applied. Then we provided some details on the attention mechanism. So we generally introduced what the attention model is. So this means that we saw how to design a scoring function which takes as input queries and keys. Then we saw how these scores are passed through a softmax nonlinearity in order to obtain the attention weights. And then we saw how these attention weights and what we have introduced as values can be combined into in an aggregate step to compute the output of the attention mechanisms. We've seen in our particular case and in many application domains that keys and values can be the same. Finally, we covered a few attention applications. So we started with the task of neural machine translation. And in this case, we introduced a model that was based on a recurrent neural network, which was coupled with an attention mechanism. And then we introduced another model, which is known as the transformer. Then we moved on into the computer vision domain, and there we saw how attention played a role in image captioning, which was an architecture which reminded of the RNN coupled with attention of neural machine translation, but which made use of a CNN encoder instead of an RNN encoder. Then we moved on to image to set prediction. So again, we saw that encoder-decoder architectures were very common. And in this case, we had an encoder which made use of a convolutional neural network, and the decoder was based on the transformer decoder. Similarly, we saw the same kind of architecture was applied in the context of image to recipe generation. And finally, we saw that in the graph domains, graph domain, attention was used to emulate convolution. So overall, what we saw in these applications of attention is that attention always follows the same principle, although like different applications differ in terms of how they define what we have introduced as query, key, and values, and in the way they define their scoring functions. I will end the presentation with the references to the papers that I've covered in the slides. And thank you all for your attention.